Cookbook for the Universe 8.16 Gravitational Alignment via Resonance. A. Resonance CRS. The Sun and Earth align through the resonance of their energy fields. This alignment is governed by the principle of superposition, where their respective fields overlap, creating a harmonized gravitational relationship. B. Dynamic bodies seeking ground. In this system, the Sun acts as a power source and the Earth behaves like an electrical coil. Through alternating current interactions, both bodies perpetually seek equilibrium ground through the other, creating a stable yet dynamic orbital path. This oscillating exchange is not static but evolves cyclically, allowing the Earth and Sun to maintain their relative positions while adapting to external influences. 8.16.1 Resonance, a superposition of fields. The Sun and Earth's gravitational fields align through resonance, defined as the synchronization of their radiated energy fields. This resonance is governed by the principle of superposition, where overlapping fields combine to create a unified and harmonized interaction. The resulting alignment maintains a consistent dynamic relationship, stabilizing the Earth's orbit. 8.16.2 Harmonic relationship. The resonance CR represents a harmonic mean between the gravitational radiated fields of the Sun and Earth. This harmonic alignment is key to maintaining the relative equilibrium of the two bodies, ensuring that their interactions remain coherent over time. 8.16.3 Dynamic bodies seeking ground. A. The Sun as a power source. The Sun radiates energy fields analogous to a power source, continuously emitting gravitational and electromagnetic influences. This radiation establishes the system's dominant energy flow, setting the stage for Earth's interaction as a reactive body. B. The Earth as a coil. The Earth behaves like an electrical coil, responding to the Sun's radiated fields by inducing its own gravitational and electromagnetic fields. This interaction creates a feedback loop where the Earth's fields adjust dynamically to maintain equilibrium with the Sun's energy. By Orion Carl Daly 1. Aka, Essay on Relative Gravity to describe the mechanics of the universe. C. Seeking ground. In this analogy, both bodies perpetually seek ground as a state of equilibrium where their respective fields balance. This dynamic process involves the continuous exchange of energy, allowing the system to adapt to external forces or fluctuations while maintaining overall stability. 8.16.4 Oscillating exchange and cyclical evolution. A. Dynamic interaction. The interaction between the Sun and Earth is not static. It oscillates cyclically as their fields influence each other over time. This oscillation is driven by the alternating nature of their energy exchanges, akin to an AC electrical system where currents and fields continuously shift. B. Adaptation to external influences. External factors, such as gravitational interactions with other celestial bodies or solar activity, for example solar flares, radiation pressure, can perturb the system. The resonance CR ensures that the Sun-Earth system adapts to these influences without losing its fundamental alignment. C. Evolution of relative positions. Over cosmic timescales, the oscillating exchange leads to gradual shifts in the Earth's orbit, axial tilt, and rotational dynamics. These shifts are subtle and occur within the framework of relative equilibrium, preserving the system's long-term stability. 8.16.5 Implications for orbital dynamics. A. Stable yet dynamic system. The Sun-Earth relationship exemplifies a stable yet dynamic system, where resonance governs the alignment and cyclic evolution of their interactions. This framework challenges the classical view of orbital mechanics as purely gravitational, emphasizing the role of radiated fields in energy exchanges. B. Broader applications. The concept of gravitational alignment via resonance could extend to other celestial systems, including multiplanetary systems, moons, and binary stars. By focusing on field interactions rather than static forces, this approach offers a more holistic understanding of cosmic dynamics. By Orion Carl Daly 2. Cookbook for the Universe. The Sun-Earth relationship is defined by resonance CR and the dynamic exchange of energy fields. Viewing the Sun as a power source and the Earth as an electrical coil, this system perpetually seeks ground through oscillating interactions. This framework not only maintains stability but also adapts to external influences, illustrating the cyclical and evolutionary nature of gravitational alignment within the principles of relative gravity. 8.17 Orbital stability through harmonic resonance. The Earth's orbit around the Sun is maintained by the harmonic mean of their interactions, ensuring coherence in the system despite fluctuations. This harmonic relationship prevents divergence and chaos in the orbital mechanics. The harmonic mean shared between the Earth and Sun in their superposition is the speed of light c, which acts as a scalar for their energy interactions. 8.17.1 Harmonic resonance as a stabilizing mechanism. A. Harmonic mean and orbital dynamics. The Earth's orbit is stabilized by the harmonic mean of its gravitational and radiative field interactions with the Sun. This harmonic relationship ensures coherence in the system, maintaining balance and stability despite external fluctuations or perturbations. B. Prevention of divergence. The harmonic resonance between the Earth and Sun prevents orbital paths from diverging or devolving into chaotic trajectories. The resonance acts as a natural regulator, maintaining the Earth's position within a stable orbital range. 8.17.2 The speed of light c as a scalar. A. Universal constant in energy interactions. The speed of light c functions as the harmonic mean shared between the Earth and Sun in their gravitational superposition. This constant serves as a scalar, linking their energy interactions and normalizing their relative energy fields. By Orion Carl Daly 3. Aka, Essay on Relative Gravity to describe the mechanics of the universe. B. Energy transfer and resonance. In their interactions, the Sun and Earth exchange energy through radiated gravitational fields. The speed of light c mediates these exchanges, ensuring that energy transfer occurs in a harmonized manner, aligning their fields in a state of equilibrium. C. Scalar influence on orbital stability. The influence of C ensures that any variations in energy output or field interactions are smoothed out, preserving the harmonic relationship. This scalar property provides a stabilizing effect, reinforcing the coherence of the orbital system. 8.17.3 Implications of harmonic resonance. A. Resonance as a framework for stability. The concept of harmonic resonance redefines orbital mechanics as a dynamic interplay of energy fields rather than merely gravitational attraction. This perspective highlights the importance of field harmonization in maintaining orbital stability. B. System-wide coherence. The harmonic mean, embodied by C, ensures that the Earth-Sun system operates as a cohesive unit, with each component dynamically adjusting to maintain balance. This coherence extends to other planetary systems, offering a universal framework for understanding orbital dynamics. C. Adaptation and resilience. The harmonic resonance mechanism allows the Earth-Sun system to adapt to perturbations, for example solar activity, external gravitational influences without losing stability. This resilience underscores the dynamic nature of orbital stability, where constant adjustments reinforce the system's coherence. The Earth's orbit is governed by harmonic resonance, with the speed of light c acting as a scalar for energy interactions. This harmonic relationship stabilizes the Earth-Sun system, ensuring coherence and preventing divergence. By framing orbital stability as a result of field harmonization and energy transfer, this approach enriches our understanding of celestial mechanics, emphasizing dynamic interplay over static forces. By Orion Carl Daly 4. Cookbook for the Universe 8.18 Energy exchange between the Earth and the Sun. The dynamic relationship between the Earth and the Sun is characterized by a continuous and reciprocal exchange of energy. This interaction is governed by the resonance of their respective fields, which enables the transfer of energy to occur seamlessly across vast distances. 8.18.1 Absorption and emission in harmony. The Earth, acting as a manifold within the Sun's energetic influence, absorbs energy in the form of solar radiation. This energy fuels various planetary processes, from atmospheric dynamics to photosynthesis, creating a system of life-sustaining interactions. In response, the Earth emits energy back into its surroundings. This emission is not merely a passive act, but a carefully modulated interaction, aligning with the principles of relative gravity. The energy emitted by the Earth interacts with the Sun's radiated fields, maintaining an equilibrium that prevents either body from dominating the system. 8.18.2 The role of impedance. The energy exchange between the Earth and the Sun is not unimpeded. Surrounding influences, such as the interplanetary medium, magnetic fields, and cosmic radiation, act as forms of impedance that shape the interaction. Impedance here serves as a regulator, ensuring that the energy exchange remains balanced. Without it, the system could destabilize, leading to runaway energy accumulation or dissipation. For instance, the Earth's magnetosphere acts as a shield, absorbing and deflecting excess solar wind, preventing the planet from overheating. The solar system's spatial geometry modulates the flow of radiated fields, maintaining coherence across planetary orbits. 8.18.3 Resonance as a balancing mechanism. At the heart of this energy exchange lies resonance. The Earth and the Sun resonate with each other, their fields oscillating in harmony. This resonance ensures cyclic stability. The energy transfer operates in predictable cycles, allowing for long-term equilibrium. Adaptive feedback. Fluctuations, such as increased solar activity, are absorbed and redistributed, preventing systemic disruptions. By Orion Carl Daly 5. Aka, Essay on Relative Gravity to describe the mechanics of the universe. 8.18.4 Cosmic timescales and stability. This energy exchange, modulated by impedance and governed by resonance, is sustained over cosmic timescales. It reflects a self-regulating system where the Earth's position and orbit adapt dynamically to changes in the Sun's field. The energy balance contributes to the stability of the broader solar system. By conceptualizing this exchange as a dynamic, field-based interaction rather than a static radiation balance, we gain deeper insights into the interconnectedness of celestial mechanics and energy dynamics. 8.1-8.5 Implications for understanding relative gravity. In the framework of relative gravity, this energy exchange transcends traditional models of heat transfer or radiation. Instead, it reveals the Sun and Earth as interacting entities within a shared manifold of relative forces. Their mutual influence shapes not only their immediate relationship, but also the stability of the entire solar system. In essence, the energy exchange between the Earth and the Sun exemplifies the core principles of relative gravity, resonance, impedance, and equilibrium. It offers a lens through which to understand not only the mechanics of our solar system, but also the universal processes that govern energy flow and balance across cosmic scales. 8.19 Implications of RG on orbital mechanics. Relative gravity. RG introduces a transformative perspective on orbital dynamics, shifting the focus from classical mechanics to a field-centric approach that integrates energy interactions, resonance, and harmonic principles. 8.19.1 Integration of forces. Newtonian gravity simplifies the relationship between celestial bodies as a direct static attraction proportional to their masses and the inverse square of their distance. RJ challenges this view by presenting the Earth-Sun system as a dynamic interplay of radiated energy fields. A. Dynamic energy fields. The Sun and Earth are modeled as radiating bodies of relative mass EC whose energy fields overlap, interact, and achieve equilibrium as Rm1d2 equals Rm2d1 equals 0. These interactions are not unidirectional. Instead, they involve a continuous feedback loop where gravitational, electromagnetic, and radiative forces adjust harmonically. B. Harmonic principles. The stability of the Earth's orbit is maintained by harmonic resonance between its radiated field and the Sun's. This resonance ensures that perturbations in the system, for example solar winds or orbital shifts, are absorbed and balanced over time. 8.19.2 Resonance as orbital stability. By Orion Carl Daly 6. Cookbook for the Universe. Rather than relying solely on gravitational attraction to maintain orbits, RG emphasizes the importance of resonance. A. Coherence through resonance. The harmonic mean shared between the Sun and Earth ensures that their fields remain in alignment. Oscillatory exchanges of energy, analogous to alternating current systems, perpetuate orbital coherence even amidst external influences. B. Implications for perturbations. Small disruptions in the Earth's orbit are self-correcting through resonance, ensuring long-term stability. Larger forces, such as gravitational interactions with other planets, are absorbed into the system's dynamic equilibrium without chaos. 8.19.3 Orbital mechanics reimagined. RGS interpretation redefines orbital mechanics beyond the simplistic view of objects moving through curved spacetime. A. Field-based dynamics. Orbits are governed by the interplay of radiated fields rather than by mass and distance alone. This provides a more nuanced understanding of planetary motion, incorporating the influence of energy, time, and surrounding forces. B. Temporal interplay. The role of time is integral to RGS framework. Oscillatory energy interactions are mediated by temporal dynamics, where the speed of light acts as a scalar for superposition and resonance. 8.19.4 Applications and broader implications. RGS principles extend the utility of orbital mechanics into realms that classical models struggle to address. A. Predicting orbital shifts. By analyzing field interactions and resonance, RG can predict how celestial bodies adapt to changes in their environment over cosmic timescales. B. Exoplanetary systems. Applying RG to exoplanetary systems reveals why some planets exhibit extreme orbital eccentricities, suggesting the role of field superposition and resonance in shaping their dynamics. C. Energy transfer in systems. By Orion Carl Daly 7. Aka, Essay on Relative Gravity to describe the mechanics of the universe. RG provides a framework for understanding how gravitational, electromagnetic, and radiative forces contribute to the energy exchange that stabilizes or destabilizes celestial systems. The RG model revolutionizes our understanding of orbital mechanics by positioning energy fields, resonance, and dynamic interactions as the foundation for stability and coherence. This shift not only enriches our comprehension of the Earth-Sun system, but also opens new pathways for exploring the intricate dance of celestial bodies across the universe. 8.20 Dynamic Adaptability. The relative gravity RG framework reimagines orbital dynamics as an adaptable, self-regulating system. It introduces a dynamic perspective on orbital mechanics, emphasizing the adaptability of celestial systems like the Earth-Sun relationship. Unlike rigid interpretations of Newtonian gravity, RG emphasizes the capacity of celestial systems, such as the Earth-Sun relationship, to accommodate variations and perturbations while maintaining overall stability. The RG framework introduces a dynamic perspective on orbital mechanics, where Earth's orbit is shaped by the interplay of energy fields rather than static gravitational forces. This adaptability allows the system to accommodate external influences, such as gravitational perturbations from other celestial bodies, while preserving its overall stability. A. Variations in orbital dynamics. Earth's orbit is influenced by factors such as the gravitational pull of nearby planets, tidal forces, and solar activity. RG accounts for these variations by modeling the Earth-Sun relationship as a harmonic resonance of energy fields. Instead of fixed paths, the framework suggests that these energy fields dynamically adjust, ensuring that the system remains balanced and coherent over time. B. System stability. Through principles of harmonic resonance, the Earth and Sun maintain a state of relative equilibrium, where their radiated fields adapt to external forces without compromising orbital coherence. This adaptability reflects the RG principle that energy interactions govern orbital mechanics, creating a flexible yet stable relationship. By emphasizing the dynamic nature of energy fields and harmonic interactions, RG offers a unified explanation for how the Earth-Sun system preserves stability while adapting to external influences. Bridging classical orbital mechanics with a field-based understanding of cosmic interactions. By Orion Carl Daly 8. Cookbook for the Universe 8.20.1 Accounting for External Forces. Celestial bodies do not exist in isolation. Their motions are influenced by nearby planets, asteroids, and other cosmic phenomena. RG provides a dynamic framework to explain how these interactions affect and are absorbed into orbital mechanics. A. Influence of neighboring celestial bodies. Gravitational interactions with other planets, e.g., Jupiter's significant gravitational pull, introduce periodic disturbances in the Earth's orbit. RG interprets these disturbances as fluctuations within the overlapping energy fields of the Earth and Sun, which adapt through harmonic resonance to absorb and neutralize the effects. B. Solar system dynamics. External forces, such as solar winds and radiation pressure, act as additional layers of influence on the Earth's orbit. The RG model sees these forces as modulating the radiated energy fields rather than destabilizing the system, ensuring the orbit remains stable over cosmic timescales. 8.20.2 Preservation of system integrity. The adaptability of the RG framework is key to understanding how the Earth-Sun system maintains stability despite these external influences. Variations in orbital parameters. A. Field interactions. Variations in orbital parameters are interpreted as shifts in the resonance of the radiated fields. By adjusting through the harmonic mean between the Sun and Earth, the system redistributes energy to counteract perturbations, ensuring long-term coherence. B. Self-regulating mechanisms. The oscillatory nature of the Earth-Sun relationship, modeled as alternating currents of gravitational and radiated energy, inherently stabilizes the orbit. Any deviation from the equilibrium position triggers compensatory adjustments, restoring balance dynamically. 8.20.3 Implications for orbital variation. RG's framework supports a nuanced understanding of orbital variation, including phenomena like eccentricity changes, axial shifts, and precession cycles. By Orion Carl Daly 9. Aka, Essay on Relative Gravity to describe the mechanics of the universe. A. Orbital eccentricity. Variations in the Earth's orbit, such as those described by Milankovitch cycles, are explained as harmonic shifts in the resonance fields. The RG model accommodates these shifts as part of the system's natural adaptability to external forces. B. Axial shifts and precession. Changes in the Earth's tilt or wobble are reframed as adjustments in the alignment of the Sun-Earth energy fields, preserving orbital stability while allowing for temporal variation. 8.20.4 Broader applications of dynamic adaptability. The principles of RG extend beyond the Earth-Sun system, providing insights into the adaptability of other celestial systems. A. Exoplanetary orbits. Exoplanets with highly elliptical orbits can be analyzed through RGS lens, revealing how their systems dynamically adapt to external gravitational forces. B. Galactic dynamics. RGS principles can explain how galaxies maintain coherence despite the complex interactions of billions of stars, dark matter, and interstellar forces. C. Cosmic stability. The framework suggests a universal adaptability where all celestial systems, from solar systems to galaxies, self-regulate through resonance and field interactions. The RG framework transforms our understanding of celestial mechanics by introducing dynamic adaptability. External forces are not seen as destabilizing factors but as integral components of a self-regulating, harmonic system. This perspective underscores the elegance and resilience of cosmic systems, offering a comprehensive explanation for their enduring stability amidst constant change. By Ryan Carl Daly 10. Cookbook for the Universe 8.21 Cosmic connectivity. The Earth-Sun system operates within a vast, interconnected cosmic network where every celestial body interacts through principles of superposition and harmonic resonance. These interactions extend beyond the solar system, linking stars, planets, and galaxies into a unified web of dynamic relationships. A. Interconnected resonance. The Earth and Sun are not isolated entities. Their energy fields resonate within the broader gravitational and electromagnetic influences of the solar system. Nearby planets, the Moon, and even distant stars contribute to this complex network, creating subtle but impactful oscillations in their respective fields. B. Superposition of energy fields. Cosmic bodies interact through overlapping energy fields, governed by the principle of superposition. This overlapping creates harmonics that stabilize and align their motions. For example, Jupiter's gravitational influence subtly affects Earth's orbit, demonstrating the interconnectedness of these celestial systems. C. Harmonic resonance across scales. From the solar system to the galaxy, harmonic resonance governs the alignment and stability of bodies. The Earth-Sun system is part of a larger rhythm, where each celestial body contributes to and is influenced by the overarching cosmic symphony. These harmonics ensure that systems remain dynamically stable while adapting to external changes. By situating the Earth-Sun relationship within this larger network, the RG framework emphasizes that no celestial system operates in isolation. Instead, cosmic connectivity, through superposition and harmonic resonance, ensures coherence and stability across the universe. 8.22 Spatial time as an abstract property. A. Spatial time is introduced as a normalized, abstract property that mediates interactions between reference frames. It embodies the concept of relative time as shared during the dynamic interplay of objects, providing a framework for understanding temporal relationships in the universe. B. The nature of spatial time. Spatial time is not tied to a single object or frame, but exists as a relational property between interacting entities. It acts as a temporal fabric through which energy exchanges and motion occur, bridging reference frames and aligning their interactions. By Ryan Carl Daly 11. Aka, Essay on Relative Gravity to describe the mechanics of the universe. C. Alternating current analogy. An analogy to alternating current AC waves helps illustrate the concept. In an AC system, in-phase states correspond to synchronized energy exchanges, where spatial time aligns perfectly, resulting in stable and coherent interactions. Out-of-phase states represent misaligned interactions, where energy transfers may fluctuate, creating dynamic but less stable relationships. This analogy provides a practical visualization of spatial time as a unifying property that governs temporal and energetic harmony between interacting bodies. D. Implications in the universe. 1. Interplanetary relationships. Spatial time governs how celestial bodies like the Earth and Sun maintain synchronized orbits and resonances. 2. Quantum interactions. At smaller scales, spatial time might influence particle interactions, reflecting the relative phases of their energy states. 3. Galactic dynamics. Across larger scales, spatial time contributes to the coherence of structures like spiral arms and galactic motion. By defining spatial time as a normalized property that operates across all scales, RG bridges the gap between classical mechanics, relativity, and quantum dynamics, offering a cohesive view of time as a shared and relational construct. 8.23 Relative time and shared properties. A. Relative time is presented as a temporal framework that contextualizes the relationships between objects or forces. It provides the basis for understanding how interactions occur across scales, tying them to shared, inherited abstract properties. extended as metaphor like the reflection in a mirror or the interplay of SE waves, emphasizes how all interactions share inherited abstract properties. The concept of RF being beyond measure aligns with its universality and pervasive effect. B. The temporal context of relative time. Relative time is not absolute but relational, existing as the connective dimension through which objects and forces interact. This shared temporal framework allows for dynamic adaptability, ensuring coherence across different scales and systems. C. Metaphors for understanding. Reflection in a mirror. Just as a mirror reflects an image that depends on the object's position and angle, relative time reflects the interplay between entities, highlighting their interconnectedness. D. Interplay of AC waves. Relative time can be visualized through the phase. By Orion Carl Daly 12. Cookbook for the Universe Relationships in Alternating Current AC Systems, where waves synchronize or desynchronize based on shared temporal and energetic properties. E. Universality of relative force. The concept of relative force RF aligns with relative time's universal nature. RF, described as beyond measure, emphasizes its pervasive effect across interactions, transcending quantifiable metrics to embody a fundamental property of existence. F. Implications of shared abstract properties. 1. Cross-scale coherence from particles to galaxies. Interactions share fundamental abstract properties that manifest uniquely depending on the context. 2. Dynamic systems. Relative time supports the adaptability of systems, allowing forces and entities to evolve while maintaining relational harmony. 3. Unified framework. By linking relative time to shared properties, RG provides a cohesive lens for understanding the universe's dynamic interconnections. Relative time, with its shared and universal properties, serves as a cornerstone of RG, offering a profound perspective on how time, energy, and interactions are inherently interconnected across all scales. 8.24 Hierarchical and Relational Model. Relative Gravity RG framework employs object-oriented principles to illustrate how abstract forces manifest uniquely in different contexts, while adhering to universal conservation laws and entropy. 8.24.1 Object-oriented hierarchy of forces. A. Abstract parent force. Relative force RF serves as the parent class in this hierarchy. B. Derived forces. Gravity, electromagnetism, the strong force, and the weak force are child classes inheriting properties from RF. C. Contextual manifestations. These derived forces adapt their behaviors based on the scale and environment, whether acting on particles, celestial bodies, or biological systems. 8.24.2 Polymorphism in programming. As an analogy, polymorphism in programming allows a parent class to have child classes with distinct behaviors. For instance, A. Fruit analogy. Just as apples and oranges are derivatives of the abstract concept fruit, gravitational and electromagnetic forces are derivatives of relative force, sharing core properties but manifesting differently. By Orion Carl Daly 13. Aka, Essay on Relative Gravity to describe the mechanics of the universe. B. Inheritance of properties. Forces retain the core properties of RF, such as symmetry and relational dynamics, while expressing them in ways specific to their context. 8.24.3 Conservation laws and entropy. A. Conservation laws. Forces operate within frameworks that preserve energy and momentum, ensuring that systems remain coherent across scales. Inheritance aligns with the principle of conservation by maintaining consistent foundational rules across derived forces. B. Entropy and evolution. Entropy drives the differentiation of forces, allowing systems to evolve from simple to complex while preserving their relational integrity. This evolutionary process mirrors the polymorphic behavior of forces adapting to unique contexts while maintaining universal principles. 8.24.4 Applications of the model. A. Particle physics. Subatomic forces inherit properties like symmetry and interaction dynamics, adapting them to quantum scales. B. Cosmology. Gravitational and electromagnetic forces govern large-scale structures, evolving to maintain equilibrium and coherence. C. Physiology and beyond. Forces manifest in biological systems, influencing processes like cellular interactions and neural activity, highlighting their universality. The hierarchical and relational model underscores the universality and adaptability of forces within RG, by framing forces as polymorphic derivatives of relative force. It provides a unifying lens for understanding their roles across diverse contexts, while adhering to foundational principles of conservation and entropy. 8.25 Applications and Universality. The relative gravity RG paradigm provides a versatile framework that applies across scales, from the merging of galaxies to particle-level interactions, offering a unifying lens for understanding the universe's complexities. By Ryan Carl Daly 14. Cookbook for the Universe 8.25.1 Broad Applicability. Galactic Interactions. RG explains how galaxies merge and maintain structure through dynamic equilibria, governed by radiated gravitational fields and resonance. Supermassive black holes, dark matter, and star systems interact as part of a shared network, maintaining cosmic connectivity. Subatomic phenomena. At the particle level, RG interprets forces like the strong and weak nuclear interactions as derivatives of a shared relative force. Quantum behaviors, such as entanglement and particle-wave duality, align with RG's principles of superposition and relative equilibrium. Planetary and stellar systems. RG reframes orbital mechanics, showing how the Earth-Sun relationship and similar systems balance through harmonic resonance and energy exchange. Stellar formation and planetary migration align with RG's interpretation of radiated fields and dynamic equilibrium. 8.25.2 Gravity as a shared property. Embedded universality, gravity within the RG framework, is no longer an isolated force but a shared property of the four fundamental forces: gravitational, electromagnetic, strong, and weak. It manifests differently across contexts, from binding galaxies to stabilizing atomic nuclei, but always reflects its foundational connection to relative force. Unified interactions. Every interaction, whether on cosmic or quantum scales, shares gravity as an inherent component, woven into the fabric of relative force. This unification normalizes phenomena previously considered distinct, revealing a deeper symmetry and connectivity. (8.25.3) Implications. The RG paradigm redefines our understanding of forces, bridging the gaps between classical mechanics, quantum field theory, and cosmology. By emphasizing gravity as a universal, shared property, it unveils the interconnected nature of all interactions, offering a cohesive framework for future exploration and discovery. By Ryan Carl Daly 15. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 8.26 Abstract Principles Applied to Merging Galaxies. Merging galaxies represent one of the universe's most dynamic and complex processes, where abstract principles like resonance, superposition, and relative equilibrium govern their behavior. Relative gravity RG provides a framework to conceptualize these interactions beyond classical Newtonian or Einsteinian mechanics, focusing on energy fields, shared properties, and dynamic equilibria. 8.26.1 Potential energy. As resonant frequency potential, merging galaxies are immense repositories of mass energy, expressed not just as static gravitational fields, but as dynamic resonant frequencies. This energy is radiated through their gravitational waves, encoding their interactions and oscillations across space-time. The resonant frequency potential between galaxies reflects their mutual gravitational influence, acting as a harmonic language through which they communicate. The merging process amplifies these resonances, reshaping the galaxy's mass energy distributions into new configurations. These oscillations manifest as tidal streams, shock waves, and the dynamic formation of new stars and black holes. Resonant frequencies continuously evolve, sculpting the galaxy's final equilibrium state and revealing the symphonic interplay of forces that defines cosmic evolution. 8.26.2 Resonant frequency. As superposition galaxies merge through the superposition of their gravitational fields, akin to wave interference. This interaction generates overlapping energy patterns where constructive and destructive resonances form distinct features. Constructive resonances amplify mass energy densities, creating dense, starburst regions or fueling central supermassive black holes. By Ryan Carl Daly 16. Cookbook for the Universe. Destructive resonances dilute regions, forming voids or tidal streams of stars and gas. This evolving superposition transforms the galaxies, with their initial spiral or elliptical forms giving way to new structures shaped by the harmonic mean of their energy interactions. The superposition model provides predictive insights into the dynamics of these mergers, such as the likelihood of forming a massive elliptical galaxy or an active quasar. 8.26.3 Unique dispositions of galaxies. Each galaxy's characteristics, mass, rotational velocity, dark matter halo, and stellar populations contribute uniquely to the merger. These properties influence formation of central structures. Supermassive black holes grow as they absorb matter from colliding galaxies, becoming gravitational anchors. Redistribution of material. stars and gas form new tidal streams or accrete into dense star-forming regions, rebalancing the galaxy's mass-energy profile. Creation of elliptical galaxies. The merger's kinetic energy and angular momentum dictate whether the galaxies form a single massive elliptical or retain elements of their original forms. This process is not uniform, but a tailored response to each galaxy's potential energy landscape, governed by their relative equilibrium within the larger cosmic web. 8.26.4 Filaments of dark matter as cosmic induction coils. Dark matter filaments, connecting galaxies across the cosmos, serve as induction coils that direct energy and matter flows. These filaments maintain the structural integrity of galaxy clusters and regulate the energy exchange between merging systems. For example, cosmic currents. Galaxies are embedded within these filaments, which guide their motions and interactions like alternating currents through a shared conductor. Dynamic influence. The Milky Way's dynamics, including its relationship with neighboring galaxies like Andromeda, are shaped by these larger cosmic currents. 8.26.5 Gravitational waves and superposition as galaxies merge. They generate gravitational waves ripples in spacetime that encode their interaction dynamics. These waves A. represent the collective energy and momentum of the merging galaxies. B. propagate as low-frequency oscillations, akin to the resonant hum of a vast cosmic instrument. C. provide a medium for superposition, where overlapping waves from multiple galaxies interact to form complex dynamic patterns. By Ryan Carl Daly, 17. Aka. Essay on Relative Gravity to describe the mechanics of the universe. Gravitational waves highlight the interplay of scale and structure, linking local interactions, stellar collisions with universal phenomena. Cosmic expansion. 8.26.6 Spatial time as the interaction as context. Spatial time, as defined by R.G., frames the interaction of merging galaxies within a shared temporal and spatial context. This concept treats the merger as an event governed by relative time, where the galaxies' interactions are measured within a dynamic, co-evolving frame of reference. Explains the temporal evolution of the merger from initial contact to final equilibrium as a continuum of shared energy states. 8.26.7 Symmetry, polymorphism, and conservation. Merging galaxies embody polymorphism, the manifestation of abstract gravitational principles in diverse forms. Key principles include A. Symmetry conservation. Angular momentum and mass energy are conserved throughout the merger, ensuring the galaxy's shared properties persist across their transformations. B. Polymorphism in action. Gravitational laws manifest as tidal disruptions, star formation bursts, and the growth of supermassive black holes, adapting to the specific context of the merging galaxies. 8.26.8 Measurement paradox and quantum analogies. Merging galaxies illustrate a macroscopic parallel to quantum phenomena. A. Superposition of states. Before precise observation or simulation, the galaxy's trajectories and outcomes exist as probabilistic possibilities. B. Collapse into reality. Measurement defines specific outcomes, such as the formation of a new galaxy or the generation of gravitational waves. This analogy emphasizes the abstract and dynamic nature of R.G., linking cosmic scales with quantum principles. 8.26.9 Implications for light and gravitational waves. A. Photon gravitational wave interaction. Photons may travel within the oscillatory ripples of gravitational waves, their paths shaped by the wave's amplitude and frequency. B. Gravitational lensing reinterpreted. Instead of spacetime curvature alone, lensing may result from the interaction of light with oscillatory gravitational fields. C. Oscillatory duality. Photons and gravitational waves represent complementary aspects of cosmic dynamics, their interplay revealing new insights into energy transfer and cosmic evolution. By Ryan Carl Daly, 18. Cookbook for the Universe. 8.26.10 Universal connectivity. Merging galaxies are not isolated events, but nodes within a larger network of cosmic interactions. These mergers A. reflect the principles of R.G. across scales, uniting solar systems, galaxies, and the universe itself through shared energy dynamics. B. provide a lens to explore the interconnectedness of phenomena, from quantum fields to cosmic expansion, within a unified framework. Relative gravity transforms our understanding of merging galaxies, offering a robust framework that integrates gravitational, electromagnetic, and quantum principles. By viewing these events as dynamic, field-based interactions governed by harmonic resonance and superposition, R.G. unifies disparate phenomena into a cohesive. By viewing these events as dynamic, field-based interactions governed by harmonic resonance and superposition, R.G. unifies disparate phenomena into a cohesive model of cosmic evolution. This perspective not only enhances our comprehension of galaxies but also provides a foundation for exploring the deeper principles that govern the universe. 8.26.11 Atomic Spectrum Analogy. Similar to atomic frequency amp velocity equals Fq, this model posits light-s oscillatory properties as harmonics of gravitational fields. 8.26.11.1 Gravitational wavelengths in extreme contexts. OJ287 black hole. Hosting 18 billion solar masses, OJ287 suggests the plausibility of gravitational wavelengths, extending billions of miles. Photons from such systems must traverse these enormous wavelengths, aligning with their gravitational framework to reach observers on Earth. By Ryan Carl Daly 19. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Compression to particles. Gravitational wavelengths could, under extreme conditions, compress into subatomic scales. Particles, like photons or electrons, may thus embody oscillations constrained by surrounding forces, such as dark matter impedance. 8.26.11.2 Theoretical implications. A. Reimagining gravitational lensing. Light bending around massive bodies could represent the interplay of gravitational wave carriers and photon signals. B. Energy transformation. The interplay between gravitational waves and photons aligns with the principle of energy conservation, emphasizing transformation over annihilation. C. Dark matter and quantum fields. Dark matter might act as a macro-quantum field, embedding oscillatory limits and regulating the relationship between light and gravity. By Ryan Carl Daly 20. Cookbook for the Universe 8.27 Spatial time. A continuum of waveforms and reference frames. The concept of spatial time redefines our understanding of time and dimension as interconnected, oscillatory phenomena. In this framework, the universe is envisioned as a sinusoidal waveform, a continuous, oscillating cycle that encapsulates the relationship between spatial dimensions and time. This perspective accommodates scales ranging from subatomic interactions to galactic dynamics, unified by the underlying wave-like nature of spatial time. 8.27.1 Spatial time across scales. Spatial time spans a vast spectrum, with wavelengths and cycles adapted to different scales. A. Microscopic scales. Wavelengths in the range of nanometers govern phenomena like atomic vibrations and quantum field oscillations. Temporal cycles operate at femtosecond or faster, reflecting the rapid dynamics of subatomic particles. B. Macroscopic scales. At larger distances, such as light years or billions of miles, spatial time governs the interactions of celestial bodies, galaxies, and cosmic filaments. Temporal cycles extend to billions of years, encapsulating the life cycle of stars, galaxies, and universal expansion. The seamless continuity of spatial time across these scales illustrates its universal applicability, integrating the micro and macro through a shared waveform model. By Ryan Carl Daly 21. Aka, Essay on Relative Gravity to describe the mechanics of the universe 8.27.2 Synchronistic events. Superposition of reference frames. Spatial time introduces the idea of synchronistic events, periods where multiple asynchronous reference frames overlap and temporarily share common properties. This phenomenon can be described as a superposition of reference frames, forming a unified temporal and spatial context. Key features include: A. Dynamic alignment. When two or more frames interact, their waveforms align momentarily, creating a synchronistic reference frame, e.g. reference frame C in the diagram. This alignment allows energy, information, or force to transfer between frames with minimal impedance. B. Impedance and collision. External factors like gravitational interactions, cosmic collisions, or quantum entanglement can induce synchronistic events. These interactions adjust the waveforms of the involved frames, creating a new shared reference point. C. Infinite probabilities. The synchronistic reference frame exists as a quanta of infinite probabilities, where the interaction S outcome depends on the specific alignment of the participating waveforms. This probabilistic nature mirrors quantum mechanics, where outcomes emerge from the collapse of overlapping wave states. 8.27.3 Superposition in cosmic and quantum contexts. The principle of superposition within spatial time unifies cosmic scale interactions with quantum scale phenomena. A. Cosmic events. The merging of galaxies with the gravitational dance of binary stars can be modeled as synchronistic events in spatial time. These interactions create temporary alignments that influence orbital mechanics, star formation, and gravitational wave emissions. B. Quantum phenomena. On a smaller scale, spatial time explains how particles interact through waveforms, sharing reference frames during entanglement or resonance. The synchronistic event provides a temporal and spatial context for these interactions, connecting quantum behavior to macroscopic outcomes. By Ryan Carl Daly 22. Cookbook for the Universe 8.27.4 Spatial time is a universal metric. A. Temporal context. Spatial time serves as a normalized property, providing a consistent framework to describe the interactions between reference frames. Whether in the nanoseconds of a photon's journey or the eons of galactic evolution, spatial time offers a unified temporal metric. B. Dimensional context. The oscillatory nature of spatial time integrates spatial dimensions, describing how objects interact across varying distances and scales. C. Harmonic continuity. Spatial time ensures continuity across scales, where smaller oscillations contribute to larger patterns, and larger patterns influence smaller interactions. 8.27.5 Philosophical implications. Spatial time challenges conventional notions of time and space by treating them as oscillatory properties rather than fixed dimensions. This redefinition has profound implications. A. Relativity of reference frames. All interactions are contextual, depending on the relative alignment of waveforms within spatial time. This principle extends relativity by incorporating wave-based superposition as a core interaction mechanism. B. Interconnectedness of phenomena. Spatial time highlights the interconnected nature of all systems, where local interactions influence and are influenced by larger, global dynamics. C. Infinite probabilities and determinism. The probabilistic nature of synchronistic events introduces an element of uncertainty and potential, allowing for emergent phenomena not dictated by deterministic laws. Spatial time as a sinusoidal continuum offers a profound lens through which to view the universe's dynamics. By integrating the oscillatory behavior of wave forms across scales and highlighting the role of synchronistic events, this framework unifies disparate phenomena within a single conceptual model. From the quantum entanglement of particles to the cosmic interplay of galaxies, by Ryan Carl Daly 23. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Spatial time captures the universe's inherent rhythm, emphasizing the dynamic, interconnected nature of all existence. A spatial time can describe the time and dimension of each frame and also when combined as a synchronistic event between the two. That is, for a period of time, like in the case of superposition, multiple asynchronous frames share common or synchronous references to each other. For the universe, whether due to an impedance, collision, or some form of superposition, the synchronistic event of spatial time representing another reference frame is considered an infinite in its quanta of probabilities. 8.28 Waveform of the universe. Expansion and contraction. Waveform of the universe. Expansion and contraction. The universe can be conceptualized as oscillating along a sinusoidal waveform, with expansion and contraction representing opposite extremes of the cycle. On this cosmic waveform, the universe's expansion and contraction could be represented as the opposite extremes of the waveform, where one side symbolizes the expansion of space-time and the other symbolizes its contraction. This model can provide a framework for understanding the interplay of forces like gravity and light within the larger context of spatial time and cosmic evolution. This oscillation could offer insight into how gravity and its relation to light interact in the grander picture of the universe. Essentially, it suggests that both gravity and light are woven into this continuous fabric of spatial time, each influenced by the oscillations of the universe's expansion and contraction cycles. 8.28.1 Cosmic oscillation. The cyclic nature of the universe's waveform depicts its alternating phases of expansion and contraction. A. Expansion phase. During expansion, space-time stretches outward, creating the framework for galaxies to drift apart. Energy radiates outward, giving rise to phenomena like the redshift of light and the weakening of gravitational influence over vast distances. B. Contraction phase. By Ryan Carl Daly 24. Cookbook for the Universe. In contraction, space-time retracts, concentrating energy and matter into denser configurations. Light may blue shift as gravitational forces intensify, potentially leading to phenomena like black hole formation or a universal Big Crunch. The oscillation between these phases suggests a rhythmic process where the universe evolves through alternating states of dispersal and convergence. 8.28.2 Gravity and light, woven into the oscillation. The sinusoidal waveform of the universe integrates the dual influences of gravity and light, revealing their interconnected roles. A. Gravity as a contractive force. Gravity represents the universe's tendency toward convergence, pulling matter and energy into denser configurations. During contraction, gravitational fields grow stronger, shaping the universe's return to a unified state. B. Light as an expansive force. Light as a radiative phenomenon symbolizes the dispersive aspect of the universe, spreading energy across vast distances. During expansion, light interacts with the stretching fabric of space-time, manifesting as redshift and the propagation of energy fields. This interplay aligns with the oscillatory nature of spatial time, where gravity and light oscillate between dominance, creating a balanced cosmic rhythm. 8.2-8.3 Spatial time and deep time wavelengths. The oscillation of the universe reflects the principle of spatial time extended to the cosmic scale. A. Deep time wavelengths. The sinusoidal waveform of deep time spans eons, encapsulating the universe's entire life cycle. Each oscillation represents a phase of cosmic evolution, from the birth of galaxies to their eventual dissolution or merger. B. Harmonic mean as a universal constant. The harmonic relationship between expansion and contraction provides coherence, ensuring that the universe maintains balance over its oscillatory cycles. Gravity and light act as harmonizing forces, regulating the transitions between. By Orion Carl Daly 25. Aka, Essay on Relative Gravity to describe the mechanics of the universe. These phases. 8.2-8.4 Implications for cosmic forces. This waveform perspective offers new insights into fundamental forces and phenomena. A. Gravitational waves. The oscillation of space-time during expansion and contraction could generate gravitational waves, carrying information about the universe's changing structure. B. Cosmic redshift and blueshift. The expansion phase stretches light waves redshift, while the contraction phase compresses them blueshift, creating observable patterns in cosmic radiation. C. Energy conservation across phases. The universe conserves energy through its oscillations, transforming potential energy during contraction into kinetic energy during expansion, and vice versa. D. Dark matter and dark energy. The roles of dark matter and dark energy might be reinterpreted as components of the oscillatory process, with dark energy driving expansion and dark matter modulating contraction. 8.2-8.5 Philosophical and theoretical considerations. The waveform model challenges conventional notions of a linear or singular universe, proposing instead a. Cyclic universes. The oscillation implies a potentially infinite cycle of universes, where each phase of expansion and contraction gives rise to new iterations. B. Interconnectedness of forces. Gravity and light are not separate entities but are deeply intertwined, each influencing the other within the context of the oscillating universe. C. Beyond the Big Bang. This model suggests that the Big Bang was not the beginning but a transitional phase in a larger oscillatory cycle. The waveform of the universe, with its alternating expansion and contraction phases, by Orion Carl Daly 26. Cookbook for the Universe provides a robust framework for exploring the dynamic interplay of gravity, light, and spatial time. By integrating these forces into a sinusoidal model, we gain a deeper understanding of cosmic evolution and the underlying principles that govern the universe's rhythmic dance across deep time. This perspective not only aligns with observations of redshift, gravitational waves, and dark energy, but also opens the door to new theoretical frameworks that unify classical and quantum mechanics within the broader context of cosmic oscillation. 8.29 Time as a derivative, spatial time and asynchronous reference frames. Time in this context is seen as a derivative of spatial time, rather than a constant measure. The idea of alternating current AC can serve as a metaphor for the relationship between time and space. Just as alternating currents in electrical systems represent a flow that shifts direction periodically, spatial time can alternate, giving rise to asynchronous reference frames as different perspectives of time and dimension depending on one's position in space. Each reference frame, for example a planet, a solar system, a galaxy, represents its own version of time, which can be thought of as a present that is relative to other frames. This view suggests that time is a matter of perspective, with each frame experiencing time differently based on its own past, present, and future. The interactions between different reference frames allow for the concept of synchronistic events, where multiple frames synchronize over time. These events could occur when two or more frames share a common connection or effect, even if their internal time scales and dimensions are asynchronous. 8.29.1 Synchronistic events and the infinite quanta of probability. A synchronistic event between multiple reference frames such as different galaxies, solar systems, or planets can be seen as infinite in its quanta of probabilities. This means that these events, while potentially infinite in their possibilities, share a kind of interconnectedness that transcends their individual temporal and spatial limitations. The interconnectedness might emerge due to a collision, impedance, or superposition, which is all phenomena that create synchronized effects across vast distances. These synchronistic events indicate that the universe itself is not static or unchanging but rather a dynamic, interwoven network of possibilities. where time and space shift and synchronize in infinite ways. 8.30 The dark fabric, a network of black holes and alternating currents. In this view, the dark fabric of the universe is composed of black holes that act like. By Ryan Carl Daly 27. Aka, Essay on Relative Gravity to describe the mechanics of the universe alternators within the spatial-time continuum. Each black hole could be seen as generating its own oscillating field, essentially contributing to the cosmic alternating current that weaves the fabric of the universe together. This idea echoes Stephen Hawking's assertion that there may be 100 million black holes per cubic light-year in the observable universe. The dark fabric is characterized by infinite probabilities, as the black holes within it continually interact with the space-time around them, creating alternating currents of energy, matter, and gravity. The speed of light as a harmonic mean could play a central role in how these black holes and their gravitational waves propagate through the universe, weaving together the vast cosmic fabric at the scale of the universe. These black holes are not merely isolated phenomena, but are woven together through spatial time via their alternating currents, creating a network that transcends the individual properties of any single black hole. The resulting structure could be a dynamic, interconnected system that shapes the overall structure and evolution of the universe. 8.30.1 Observation: the universe as a unified oscillating continuum. In this theory, the universe is viewed as a dynamic continuum of spatial time, where time and space are in constant flux, expanding and contracting in cycles. The four fundamental forces are woven into this continuum, with gravity and light serving as integral components that influence the behavior of matter and energy. The dark fabric, composed of black holes and their alternating currents, acts as the medium through which the cosmic forces interact and synchronize across vast distances. This view offers a novel perspective on the interconnectedness of time, space, and gravity, where the universe is not just a collection of isolated bodies but an intricate, oscillating web of interacting forces and probabilities. By Ryan Carl Daly 28. Cookbook for the Universe. 8.31 Symmetry and Polymorphism in Evolution. The theory also incorporates the idea of symmetry in the evolution of the universe. It suggests that symmetry is conserved in the properties derived from the fundamental currents. The properties of the universe evolve through polymorphism, meaning they can take on different forms depending on the interactions of the underlying currents. This evolutionary process is shaped by the currents and forces at play. In this framework, the universe evolves in patterns that are both symmetrical and random, allowing for the development of diverse properties and forms. Randomness, in this case, is not a complete negation of order, but rather a way of introducing variation within an underlying symmetrical framework. 8.31.1 Symmetry and Randomness, a dynamic relationship. The relationship between symmetry and randomness in this theory allows for a flexible and adaptable universe. Consider, for example, the lighting of a light bulb. It depends on the flow of current, but the exact moment at which current flows may seem random. Yet it still adheres to the overall symmetry of electrical currents. The same principle of symmetry governs opposite charged particles, which can interact with one another in ways that maintain the overall balance and equilibrium of the system. 8.32 Absolute Zero and the Harmonics of Strings. In the pursuit of absolute zero, the theory introduces the idea that the same symmetry that governs particles and charges can also extend to strings, which, in theoretical. By Ryan Carl Daly 29. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Physics are considered the fundamental building blocks of matter. These strings are not static but can have harmonics, akin to the vibrations of a musical string, allowing for a rich diversity of states and behaviors. The symmetry of strings underpins their oscillations, creating a dynamic system where the interactions of particles and forces can be modeled as resonant frequencies or harmonics within a larger cosmic system. 8.33 Conclusion: a new framework for the universe. While this theory may seem unconventional and controversial, it offers a new lens through which to understand the universe. By viewing the universe as a network of alternating currents and integrating symmetry and randomness, the theory proposes a dynamic and evolving cosmos where forces, particles, and energy are interconnected in a complex web of relationships, continuously shaped by the underlying currents of existence. 8.34 Common and Inherent Properties of Force, a Unified Theory. The theory of relative gravity proposes that the relationship between dark matter and light matter can be understood in terms of impedance. This analogy frames particles, galaxies, and any objects in between as manifolds, geometric structures that carry common and inherent properties of force. These properties are viewed as interwoven, allowing for complex interactions across various scales. from the smallest particles to vast cosmic bodies. 8.35 Particles and harmonics, opposite charges and string vectors. In this framework, particles may have opposite charges, yet still be harmonically related through strings. The concept of strings is akin to the vibrations in a medium, where the forces between particles can be interpreted as oscillations or waveforms. These oscillations are vectors that interact, creating harmonics patterns that are part of the larger continuum of forces. 8.36 Wavelengths, time and transformation. The theory suggests that wavelengths, whether associated with light, gravity, or other forces, can undergo distortion in time. This distortion does not erase the inherent properties of the waves. Rather, the properties are retained and transformed across time. In this view, time itself is a dynamic, derivative property. Time can produce other time, further influencing how forces and particles interact. This perspective allows for bodies to be skewable and cumulative with respect to each other, suggesting that their interactions are influenced by their relative positions and frames of reference. Gravity, in this context, is not just a force of attraction but is, by Ryan Carl Daly 30. Cookbook for the Universe. Defined by the relationship of bodies to each other in superposition, meaning that the influence of one body can overlap with another, creating a complex network of forces that affects the behavior of everything in that space. 8.37 Philosophical undertone. The essay has a philosophical angle, reflecting on the abstract and the concrete. For instance, the idea that we are concrete examples of shared abstract principles gives a humanistic dimension to relative gravity, suggesting a deep interconnectedness between all things. 8.38 Polymorphism and the principles of the delta phenomenon. The concept of polymorphism in this abstract model is applied to the unification of physical laws and the nature of entities in the universe. It proposes that entities, whether particles, bodies, or larger systems, undergo transformations and cycles in ways that preserve and express their properties through varying states, much like an alternator generating alternating currents. This dynamic is formalized as the delta phenomenon, a model that describes how an entity exists across different states, both in time and dimension, with a focus on the cyclical evolution of these states. 8.38.1 Key principles of the delta phenomenon. The basis of dimension in a body. The delta phenomenon serves as the fundamental basis of dimension that underlies all entities. It proposes that the physical properties of bodies and systems are not fixed in a singular state, but are instead subject to transformation, allowing them to exist across various states of being. Existence in prior and future iterations for an entity to be observed in its present state. There must also be a prior and future iteration of that entity. If an entity exists at a given moment, its history, prior iteration, and potential future iteration must also be considered. The current state of an entity cannot be fully understood without accounting for its existence across time. The family of entities and unique personifications. The delta phenomenon applies to both singular entities and families of entities, where each may exhibit a unique manifestation of the phenomenon. However, despite these unique expressions, they remain part of the same underlying delta phenomenon. This means that different entities or systems, though varied in their specific characteristics, still share a common underlying principle of transformation. See parallelism and symmetry across entities. Even though entities may be unique in their manifestation of the delta phenomenon, they parallel each other through the symmetry of their cyclical nature. This allows for, by Ryan Carl Daly 31. Aka, Essay on Relative Gravity to describe the mechanics of the universe. The establishment of points of reference between different categories of existence. The uniqueness of one entity or system is linked to the others through the principle of symmetry, where even radically different systems can share structural parallels, thus making comparisons or correlations possible. (8.3.8.2) Application of principles in evolution. These principles can be viewed as an object-oriented model for evolution, where the evolution of entities, whether they are particles, organisms, or galaxies, is understood through the lens of polymorphism. Polymorphism, in this sense, refers to the ability of an entity to express different states or forms across time, all while maintaining a coherent identity or set of properties. Cyclic paradigm. The principles function in a cyclic manner, similar to Mandelbrot sets or the Sierpinski triangle. These fractals repeat in self-similar patterns at different scales, and the principles of the delta phenomenon similarly repeat in cycles. The progression of these principles follows a pattern from Principle 1 establishing the basis of dimension to Principle 4a establishing symmetry and reference across entities, then back to Principle 1 as a new cycle of differentiation. Inheritance and differentiation. The polymorphism of entities occurs through inheritance of properties from earlier stages in the cycle. As an entity undergoes differentiation through time and space, it retains properties from its previous iterations, and these properties evolve as the entity progresses through each stage. 8.39 Linking to Weinberg's Singularity in Scientific Law. By Ryan Carl Daly 32. Cookbook for the Universe. The model proposes that polymorphism offers a reasoned framework for understanding the singularity concept, similar to that of Steven Weinberg's singularity in physics, while the traditional Big Bang theory views this event as the singular origin of the universe. Polymorphism introduces a more dynamic perspective. The Big Bang is plausible, but does not necessitate a singular beginning. Instead, it suggests that the universe operates within ongoing cycles of transformation, where multiple Big Bangs may occur as part of the delta phenomenon's eternal continuum. Polymorphism enriches this framework by emphasizing the inheritance and conservation of properties across cosmic cycles. It allows forces and entities to transform while retaining core principles, bridging classical, relativistic, and quantum mechanics within a unified framework. In this context, scientific law and observation remain pivotal as they validate the cyclical and evolutionary aspects of these transformations. 8.39.1 Relative Gravity and the Big Bang. Relative gravity (RG) reinterprets the Big Bang as more than a singularity. It is a moment of gravitational field superposition where immense energy and matter condensed, initiating cosmic evolution. In this view, the Big Bang represents a state of equilibrium within an infinite series of cosmic cycles. The interplay of gravitational waves, energy fields, and the delta phenomenon defines this evolution. A. Gravitational waves as a foundational element. The Big Bang manifests as an immense gravitational superposition, generating waves that radiate outward, laying the groundwork for matter-energy clusters. B. Galactic formation and equilibrium. Structures like the Milky Way form as localized zones of gravitational equilibrium, where radiated fields align to create spiral galaxies, torqued arms, and ordered systems. 8.39.2 Orbital Dynamics within Galactic Threads. By Ryan Carl Daly 33. Aka, Essay on Relative Gravity to describe the mechanics of the universe in galactic threads. Solar systems follow patterns dictated by radiated gravitational potentials. A. Hierarchy of radiated fields. Suns and their planets orbit galactic centers while maintaining internal equilibria. Smaller systems remain closer to galactic cores, while massive clusters orbit at greater distances, consistent with B. Interstellar currents. Galactic arms behave like induction coils, where gravitational currents stabilize systems. These currents mirror electrical currents, enabling solar systems to follow predictable, harmonized paths within the galactic structure. 8.39.3 A unified cyclical model of the universe. The delta phenomenon underpins a cyclical universe model, where forces and entities evolve over infinite iterations. A. Inheritance of properties. Across cycles, the universe's forces, for example gravity, electromagnetism, transform while conserving fundamental traits. B. Polymorphism of forces. The Big Bang unifies fundamental forces, which evolve uniquely across iterations, reflecting their relative context in time and space. C. Time is a cyclical continuum. Time viewed as spatial time flows cyclically. Each Big Bang marks a shift in temporal reference frames rather than the genesis of time itself. 8.39.4 The Big Bang and the Delta Phenomenon. A. The Big Bang as an iterative cycle. The delta phenomenon portrays the universe as cyclical, where the Big Bang represents one iteration. This event symbolizes an immense energy emergence from a singularity, initiating a transformation. However, it does not signify the beginning but a transition in a continuous cosmic cycle. Entities evolve polymorphically, inheriting properties from prior iterations and contributing to future cycles. B. The Big Bang as dimensional transition. Instead of creating space, the Big Bang transitions the universe from one dimensional state to another. The expansion of space-time reflects inherited dimensional properties, evolving from prior iterations. This principle aligns with the delta phenomenon's framework of transforming entities while retaining their core essence. C. Polymorphism and symmetry. Polymorphism ensures that forces entities evolve cyclically while conserving symmetry. Although unique, each Big Bang follows patterns of expansion, matter formation, dimensional evolution, reflecting the universe's underlying symmetry. 8.39.5 The Big Bang as a part of a larger polymorphic universe. By Ryan Carl Daly 34. Cookbook for the Universe. The Big Bang is neither isolated nor singular, but part of a larger system of cosmic rebirths. In this model, A. Properties are inherited. Energy, matter, and forces recycle through cosmic cycles, ensuring continuity across iterations. B. Polymorphic forces. Unified forces undergo transformation while retaining a relative relationship. C. Time is cyclical. Each iteration redefines temporal frameworks, contributing to the universe's continuity. 8.39.6 Parallels to Steven Weinberg's early universe and Steven Weinberg's The First 3 Minutes. The universe's cooling and evolution mirror principles of thermal and gravitational dynamics. A. Adiabatic cooling. Both the early universe and solar winds exhibit adiabatic cooling, where expansion reduces temperature and density. B. Energy redistribution. Energy distribution patterns in the cosmic microwave background CMB parallel solar wind harmonics, emphasizing resonant processes. C. Plasma dynamics. The primordial plasma transitions into neutral atoms akin to the solar wind disk transition in interplanetary space. D. Observable signatures. The CMB heliospheric current sheet reflect thermodynamic transformations, revealing parallels in energy redistribution across scales. 8.39.7 Resonance and solar wind dynamics. Solar winds provide an analogy to the universe's evolution. A. Thermal resonance. Solar winds transfer energy, aligning with Carnot cycle phases and the universe's cooling. B. Gravitational resonance. Black holes amplify this resonance, transforming mass energy into high-energy emissions like quasars. 8.39.8 Black holes as spatial induction engines. Relative gravity positions black holes as cosmic induction engines. A. Energy compression. Gravitational forces convert energy into extreme densities. B. Wave-particle resonance. Plasma flows align with space-time curvatures, creating resonant frequencies. 8.39.9 A unified cosmic framework. By linking the Big Bang, delta phenomenon, relative gravity, redefines cosmic evolution. The universe is an interconnected system of cycles. Forces transform while conserving core principles.